This is so exciting. I think I found it. A couple days ago, a coworker sent me a blog post, two-part blog post on something called Mu. I believe that's how, I believe he's intending to pronounce it, like the Greek letter. But so I've been building this 8-bit, designing and building this 8-bit processor. The building part is fairly early in the process, but designing it's come a pretty long way. I've already gone through several iterations, and my first iteration, I had an instruction set that was designed for this processor, and I had it functioning and working, and it was actually it was in the simulator working, and I started writing a code, a program, a function called for it to execute, and I realized I had kind of made a fundamental flaw in my instruction set architecture. And what that meant was that function calls were actually really expensive, way more expensive, proportional to the rest of the code than I was comfortable with, and difficult to kind of architect in a way that was flexible and useful. So that started me on a quest to find how to simulate some program on this architecture that I was designing, so that when I got to that point, I spent all these hours and all this money building this computer, and I got there and I started trying to design a program to run on it. It wouldn't just be a complete disaster. And I mean, if I had built on that initial architecture, it would have been basically a large brick that was a novelty that I could show off for a few friends, but that's about it. So, long story short, I started this quest, and I think I finally found the last piece in the puzzle to figure out how to design and simulate programs for this architecture. And so, at any rate, I got this 2-part article, and it was the missing puzzle piece. And so I got really excited. I had to create a quick vlog for it. Jotted some kind of props down here on some paper, and I'll just take you through kind of the three major steps I've gone through in arriving at the conclusion that this is what I've been looking for. Early on in the process, I assumed that I was going to use something like the Arduino IDE and treat my processor as a microcontroller, and I would just need to build the interfaces and adapters to basically compile C code, so I'd have to provide it with the compiler, and then the drivers to connect the IDE to send the code to the memory of the device. So that led me to, how do I write a C compiler? I don't really want to write a C compiler from scratch, right? I mean, that's a lot of work, and a lot of people have kind of spent a lot of hours doing that already. So that led me to LLVM, which is according to them, a minimal dependency. Sorry, wrong quote. According to them, a collection of modular and reusable compiler and toolchain technologies. Yeah, it's kind of a mouthful. So it's basically a very complex stack built for modern computer architectures for compiling C, C++ programs. And the way it works is, let's hold this up. The way it works is you get your code, and then your code gets translated into this LLVM intermediate representation, IR, LLVM IR. And then this is kind of a one-to-one, there's a mapping here that you have that LLVM is written, or a provider of a language. So C, C++, Swift has one, Objective-C, because Apple uses LLVM on their mobile devices and their Mac platforms. It's their compiler of choice now. So anyway, then a whole bunch of magic happens. Now this is, who knows, like all kinds of different things happen here that don't really tell you what they are. I mean, I know roughly what, it does instruction unrolling, it does instruction reordering to optimize for memory access and those types of things. There's a whole bunch of suite of things. And so it piles a bunch of layers of optimizations and spits out LLVM IR again. So at this point though, it may not be really recognizable with the C code or whatever code you sent in. And then the next step is that the LLVM IR code gets sent to the code generator for whatever computer architecture you have, and then it spits out the binary for execution on that architecture. So the problem with it is it's really, really, really complicated. First of all, this magic piece here, this is really frustrating for me, because what I'm trying to do is build a simple computer, something that a single human can kind of understand, can grok at a very deep level all the way through the stack, from the operating system, even all the way up to application layer, all the way down to the instruction set and the logic level. It necessitates being very aggressive about being very, very, very simple and having a simple architecture. This is like a massive black box of magic, and there's no way that having everybody who wants to use and build on top of this CPU is going to be able to use LLVM or understand how it works. And it's just kind of like this magic black box that is functionally, technically it compiles, but it's not really what I'm going for. So I started trying to look at what I could do to design my own language, write my own compiler. I wrote an assembler to, basically something modeled on a typical assembly language that would write it. That's actually how I did my. I started writing assembler so that I could write my test code, and that's how I figured out my architecture. My instruction architecture was wrong. So at some point along the way, while I was trying to figure this out, one of my friends told his dad about my project, and he immediately said, "Hey, I recommend you use Forth." And I was like, "I've never heard of Forth. What is Forth?" And I was like, well, my first instinct was like, oh man, this is, everybody has something that they recommend that's their favorite thing. But turns out, actually, he knew what he was talking about. Apparently, he's a 8-bit computer hobbyist, ongoing, and has been for a long time. So he kind of knew what he was talking about, and he had an old 8-bit computer that was unable to run a lot of stuff, but one of the things it was able to actually run was Forth, and he kind of messed around with it a bunch. Now, Forth is a stack-based language, and this is kind of one of the problems with it is you actually have to, you don't program in Forth the typical way that you think of in a functional programming language. A functional, not mean it works, but functional as in a functional style of programming. So because it's a stack-based architecture, you write things in reverse Polish notation, basically. And so this is a simple example of how you would add two numbers. And so you would have the first number, the second number, A and B, and then plus. And so what happens is A gets pushed on the stack, B gets pushed on the stack, and then the plus pops these two off the stack and pushes the result onto the stack. And so normally, and so it uses this data stack to pass arguments between functions. And normally programming languages don't intuitively work this way. You would say something more like result equals A plus B. instead of this AB plus and then just know that the data is on the stack. The cool thing about this is it is really, really easy to write this, implement this in hardware. And so I was really, really attracted to this because it allowed me to really kind of focus on, I could write some optimized hardware for this kind of programming language. And then using Forth, I could actually write higher level languages on top of it. So this was a lot closer. I read a book on Forth in a couple hours, and I understood it well enough to understand how to write it. And there's details to work out and some nuance that I had to, some things I would have to resolve. But by and large, it was a huge, huge step in the right direction. And so that's what I've been intending to do, is use maybe not precisely Forth, but something like Forth. And then one of the things I was churning over in my mind is how to, Forth, by the way, is Forth. It's not fourth as in like the fourth person or the fourth number. It's Forth as in Forth, if you want to Google it. So anyway, so I was, one of the things I was mulling over was how do I make this programming language accessible to a lot of people? And the one problem with Forth is it was kind of going to be a left turn for a lot of people, and I wasn't sure how much, how broad the appeal for that was. I mean, Forth has a very, very passionate community around it, but I wasn't sure how broad the appeal of using programming in Forth was going to be to a lot of people. So again, it was like this kind of barrier between the high level language and the low level machine code that the processor needs to execute. So I was thinking I could make it work, but still a little uncomfortable. So then comes along this 2-part blog post, and I knew I was going to like it from the moment I opened the article and read the lead-in quote. And the lead-in quote is, "It is far better to have an under-featured product that is rock solid, fast, and small than one that covers what an expert would consider the complete requirements." That is a quote by Richard Gabriel from his book, Worse is Better. And so I'd never seen that quote before. This is actually one of my fundamental driving philosophies for programming that conclusions that I've come to, is that we've made things way too complicated. We've added all these features, and the lion's share of the features that we add, we don't actually use to their full capacity. And in fact, we don't have the ability to support most of the features that we add. And this goes for small companies, this goes for big companies, small teams, big teams, it doesn't matter. Because you always tend to produce more features than you could support in a coherent and a consistent way. There's a few companies who I think of, I'm blanking on the guys who did Basecamp. They are like super, super diligent about, why can't I remember the name? So anyway, they are super diligent about creating applications that are as feature simple and yet powerful and like focused and purposeful as possible. And it served them very, very, very well. That's really one of the things I'm advocating for. And in building this 8-bit computer, that's really what I want to do. Is I want to build one of the simplest architectures I can that can drive an actual usable desktop computer. That's my ultimate goal, is to be able to have a desktop computer that one person can understand from the application layer all the way down to the logic gate level. And it's going to have to be dirt simple. I mean, super focused on keeping it as simple as I can. So I came across that quote and I was like, man, under-featured product that is rock solid. Like that's what I'm trying to do. That's under-featured. That's why I went with 8-bit. I'm trying to capture it. You know, these old 8-bit computers, they you just turn them on and then you're typing into the computer and it's there, and you have direct access to the machine, and you can touch every part of it just by writing a few commands, and you can turn, you know, this register on, put this value in this register, and it affects this, you know, what the video mode or the sound or whatever it is, or the graphics, or you can put a character on a screen, or all these different things. But a human being, one single human being, can understand it all the way through. Well, most of the way through. The one thing they did lack is a lot of it was proprietary. The operating system itself was proprietary. It was fairly simple to figure out how it worked, but I want to do the OpenStack all the way through. Ultimately, I'd like to be able to build an actual processor, but all my research, that's prohibitively expensive. So, getting back to Mu. He has 3 levels. He's building 3 levels. The first level is just the processor's instruction set with some syntactic sugar built in. So what I'm going to do is I'm going to take, he's using the x86 architecture, which is, you know, Intel's architecture that's, you know, really old by this point. It's evolved over time to a 64-bit architecture, but he picked a common subset of instructions, and those are the instructions that the language supports. So I'm going to take that approach. I'm going to take the syntactic sugar that he's developed, and the approach and the compilation, and I'm going to lift it and put it on my 8-bit instruction set. And then I can build all of that in software and then simulate before I actually build the internal CPU controller that actually does the execution. I can still move forward on the other pieces I'm doing, like building the 8-bit adder, building the registers, building, like, all those components are, the instruction set's not going to affect much. But by the time I get to actually building the controllers, the logic controllers and the internal, like, jump instructions and all that, I want to be able to simulate this in software. So I'm going to take his syntax, and here is the level 1 example of level 1. And if you're not a programmer, don't worry. But the key thing here is this is the opcode 89, and this is really a comment. The compiler doesn't pay any attention to this. This is just a comment to, it could be it doesn't have to be this little arrow. It could be a text or whatever you want. That's kind of a comment describing what this instruction code is. In this case, it is a store, so it's taking this value and storing it in this register. But the idea is then it takes instruction code 89, which takes 5 of this type, which is RM32, which is the indicator that it is storing the value in a 32-bit register, basically. And it's just by comment, it's the EDP register, which means something it's a certain register name in the x86 architecture. So, but it happens to correspond to number 5. And so basically this and this are required. This is the comment, and the same here. This is number 4. It's reading from register 4, which is the, what is that, ESP? Yeah, ESP register, and it's R32. And I won't go into the details, it's not important. But you can see how this is very, very close to the instruction set, the machine code. But once you get used to the slashes and everything, the syntax is fairly readable. And here's one of the cool things that I really, really love about his design decisions. He goes through this whole thing of why he chose the opcode here. Like, he left the opcode number there. and largely because you don't have to have any additional structure or programming or to translate the opcode, some mnemonic value into the opcode, and you just learn the opcode. And I really, really, really like this because you should be able to, the instruction set should be simple enough that you can remember all of the opcodes you need or look them up very, very, very simply. And you shouldn't have to have thousands of opcodes or anything like that. And you should be able to very simply write these instructions, and over time you can get used to this, but you don't have to you don't have to translate this into text and divorce yourself from the underlying opcodes and structure of the instructions. So I really like this because it keeps you close to the hardware, and I think this is elegant. My architecture is a little bit different, but if I translated it into my architecture, it would be something like this, where it's 5, which is one of my, it's not exactly the same as 89, but it's one of my move a value between register. And then, so it says move, this is the accumulator register. This is just a comment that says, hey, I'm doing this into the accumulator, which is a register that's kind of like the default destination. And because I have so many, with an 8-bit CPU, you have very limited instruction sets. So I made some architectural decisions where you can't go from an arbitrary one to an arbitrary one. But that's, we'll deal with the architecture later. But this video is really about kind of the language. And so then register 4 it's an 8-bit value, and XYZ is just whatever comment you want there. So that's an example of how I would do that. And then I can write the code to support it. And then once you get that, he's working on level 2 right now, which is the memory safe language. And this is kind of a higher level stuff that starts to get into the higher level feel. And I haven't dug into this one too much yet, and I really want to. But my idea is that I'm hoping once I get into the weeds and the details that I could take this and then use the same technique to apply his higher level language directly to that, and then leverage everything from level 2 up, which is level 3 then becomes an expressive high level language is what he's aiming for. So memory safe and then expressive high level language. And I'm hoping that I can just write this level 1 piece with a similar kind of structure plus the syntactic sugar, which I didn't go into there much. That's just a flavor of it. There's other things too. And then tie that into level 2, and then we have this great programming language running on the CPU. And so this will give me if I build level 1, it'll give me the ability to test and make sure that my instruction set works and you can actually write real programs in it. And I can start to get there and make sure I can implement the syntactic sugar and all that stuff. And so I'm so excited about this. This is going to be good. It's still going to be a little bit of work none of this is really super trivial, but I think it's at least understandable. And so don't worry about it. If you didn't understand that too much, I'm going to go through the instruction set over time in much more detail, and I'll go into the design decisions and why certain instructions are there, why I made certain choices, and we'll do that in other episodes. But I just wanted to take this opportunity to kind of walk you through my thinking on the instruction set architecture. So I'm really excited about this. As usual, like and subscribe if you liked it, and if you hit the bell notification, you'll get reminders about when I launch my next videos. I'm gonna do one on, I think one of my next ones is gonna be on me actually soldering and putting together and testing my 8-bit adder to see if it works. So hit that bell to notification to see that. Leave comments and I'll try to respond to the comments if you have any questions. I will leave in the description. I'll leave links to all the things that I referenced, and you can also support me on my Patreon page. Help me set aside time to do this work and get all the resources I need to accomplish this. It's not free. And until next time, do you grok this?